Okay, I think I'll start recording. So just a quick reminder. So the exam is next Monday. I sent you yesterday like a study guide for the exam. The only thing that's like, well, you should check all the study guide, but especially like the beginning of it because there I mentioned explicitly which formulas I will give you on the exam. So kind of at the beginning of the exam where you have like the general instructions, I'll just put those down. The only thing is like I won't put them with their specific name, so you just have to know. Like I'll give you like the formula for the Bayes theorem. That's one of those. It's just I won't put like the name Bayes theorem next to it. I'll just put like the form what the formula says. So just check on the study guide which formulas I'll give you. Um, so that you don't have to memorize them, but at least you should know how to recognize them. Um, and then, yeah, I gave you some extra problems, but basically, the thing I was realizing is like, kind of like all the many problems are just start getting a little bit too repetitive. So, like, if you just check like the problems I recommended from the study guide with those other four problems that I sent you yesterday, I mean, I think you more or less like the exam won't be that different from like what we have been doing. So yeah, just check that. Like like conditional probability and is an important thing. So and the other like stuff we have been doing with random variables. It's only the discrete part of the random variables. So all this new stuff we have been doing. I'll do 3 and 3. I think no more than 3 on each part, but I think now we do have enough material to ask like 6 questions. I feel like maybe the first exam again, it was like if I had 6 questions, like it was too repetitive, but I feel for this one, 6 should be enough. But if I end up doing, I wouldn't go beyond 6. So, but I think, yeah, probably 6 will be the number I will go with. Or yeah, I have to if um I think 6 between 4 and 6 for sure, but I'm going more for 6 at the moment. But I could end up doing 5 as well. But yeah, I just have to check how like I don't like to ask like the same question twice. So like I'll definitely put like like a question about entropy, probably like must like we have like something about computing like an expected value of a random variable or something like that. That's 2, and then like I can easily put 2 on like this conditional probability stuff Bayes theorem, independence. Like yeah, I think I can manage like 5 or 6. So um, but yeah, it will be split like 3 and 3. So uh, so uh, just to remind you what we were doing yesterday. So no, not yesterday. Wednesday, 2 days ago. So we spent some time talking about this Gaussian or this normal distribution, which is the other name that's given to it, just because like you'll see towards the end of the course, it's really it's like a very important distribution because it's related to what's called the central limit theorem, which we'll spend like again, that will probably be almost like the last class of the course talking about that. So that's why it's called normal. The normal distribution because it's kind of very typical distribution that will appear in probability problems. So we computed its expected value and its variance, right? Well, in this case, like it was symmetric. Like I gave you like the formula that's symmetric about the origin. So like the average or the expected value was just 0. The variance is slightly more interesting. It was just the variance was just k. So the other way in which, if you want to write it in terms of the standard deviation, that's This is typically what you'll see. Okay, so that's like the famous Gaussian, and well, what I told you kind of at the end of the class last time, um, for during class was like one way to think of how one way to find it is that there is some sort of like entropy that you can define in the continuous case, um, and the Gaussian happens to be the distribution or like the probability function with the most entropy amongst those. You have to imagine that you fix like the standard deviation. So assume that you know the standard deviation. You can also assume that you know the average. So imagine that you know the average and the standard deviation. So among all the probability functions with the same average and standard deviation, or variance, the Gaussian is the one with largest entropy. So it's kind of like a maximizes like a quantity. So that's one way to think about how it would appear. That's very like a very elegant way to think about it, um, because it's kind of like a maximization principle, um, which are like very common in nature. Like there's like this math principle that when light goes from one point to the other, it takes the path of least time and things like that. So like there are many like optimization principles that get used in the sciences, and so this is kind of like analogous to those, where like it's like the Gaussian is like among all distributions, the one with the most entropy. Okay, so that makes it important from that perspective, but there's like a more concrete perspective that makes it important. It's more closer in spirit to what the central limit will say later. So the other way in which the Gaussian appears is by approximating the binomial distribution. So that's kind of useful to understand because it just will give you like a different flavor for like the types of probability arguments that we will care later towards the end of the course. So here's like let's talk about that. So let's start by talking about the Gaussian or about normal distribution. Uh, well, it is like it depends on how you phrase it. Like what happens is that amongst you know, it's like a pro. It is kind of like the thing is like I mean this will become actually more clear once I do this from this other approach. It, the thing is like the equilibrium, like what's called the equilibrium, is kind of like in a sense like the nature can be in different configurations. It's just that the what's called the equilibrium solution, or the what corresponds to like the thermodynamic equilibrium, is overwhelmingly the most likely option. So it's not that like it is necessarily evolving towards equilibrium all the time. It's more like that any fluctuation from equilibrium is so unlikely that for all practical purposes it's kind of approaching like equilibrium. But there's no I mean, yeah, this is related to this second law of thermodynamics thing. There's nothing like against, like in the laws of physics, for example, that would prevent a cloud. I mean, the usual example of the second law is like if you have like a cube of ice, right? As time goes by, um, the ice will start melting, right? The reverse process where like, you have a bunch of ice, you just have a bunch of water on your table, and that sort of kind of like starts like rematerializing into a cube of ice is something that for you kind of never observe, right? That's kind of like the reverse, like the it's kind of playing like the movie backwards, right? Like if you saw like a bunch of water recondensing into a piece of glass, sorry, into a piece of ice, that kind of doesn't happen. But it's not because it's kind of like forbidden by the laws of physics. It's just like the probability, if you do like a probability argument, like the amount of coordination between the different particles to recombine into a molecule of ice is so extremely unlikely that for all practical purposes you don't know, you would never observe it. So it's not that it will always like go towards equilibrium. It's just like that the equilibrium solution is kind of all the possibilities for your system, is kind of the one that takes the most space in a precise sense. uh, it's like the most likely, and so that's kind of like the one you end up running into in practice. So it is like a subtle topic, but yeah, it's related. I think I sent you like a video of the second law if you on one of the announcements. So it's all related to this question about you know, whether like the second law is true exactly. The second law says that the entropy always increases. That's a classical version of the second law in an isolated system. But then there's this question is whether is that actually always true, or is it just true on average, or like uh probabilistically speaking. So yeah, it's but yeah, like in a sense, like it does prefer. I mean, in many cases, it will prefer like the Gaussian distribution, but only in the sense that any deviation from the Gaussian it would be allowed to happen. It's just that it's overwhelmingly unlikely. So for all practical purposes, you can kind of live, without being too worried about that. But yeah, it's like a complicated topic. And also remember, like, yeah, you have to be careful. I mean, yeah, it's like a long topic, but it is an interesting topic. But I would just put it like, it is kind of like the preferred one if you allow for deviations to happen, but it just happens that since you're dealing with so many particles, the number of like deviations from the Gaussian are is extremely unlikely. So this will become more clear. Like what I mean will become a little bit more precise in a second when I tell you a little bit more about how to get the Gaussian from the binomial distribution. Uh, so so okay, let me put it like this way. Let's say just to make it just to make the numbers a little bit easier, like let's say that you have two n particles. So you have two n particles. Uh, and you have like a container. Let's say symmetric with respect to the origin. So like, you put like a container of certain length. Like the length won't make a big difference right now. It's just to kind of like make it like a little bit more like, to make it a little bit more concrete. So here you could have a container of length L. So it is perfectly symmetric about the origin, so meaning that half the length is to the right of the origin and half the other length is to the left, right? Symmetric about the origin. So you could say, well, for each particle, right? So let's say that for each particle, like let me draw some balls, like here's how you could think about them. Right, so in this configuration, I have three particles on the left side and four particles on the right side, right? So in this case, I'm having, I'm using like an even number. So just to make it even, let me put, yes, so now what I have, okay, now I have three and I have five, so now I have a total of eight. It's just more convenient to have like an even number of particles in this case. So, you know, like eventually I will, so here I just have eight particles. Eventually what will happen is that we want like to think of that n is going to be really, really large, right? So later, like in a couple of minutes, soon n will be very large. Large, like in the sense that what you see in your chemistry class, like of the large in the order of the Avogadro number. So like Avogadro number. I don't know if I saw how you spell the name. So like 10 to the 23 or 10 to the 24 particles, that order of magnitude. Okay, so it would be a humongous number of particles, right? A huge number. So But like since like container is perfectly symmetric, you might say, well, each particle has probability one half of being on each side of the container, right? So P, uh, which is one half, will be the probability, say for a particle to be on the right side of the container. So if you remember, like we could define like a random variable, which was like the number of like we could say we could have like this random variable, which was the number of particles on the right side of the container, right? This is like what was this? This would be like a binomial random variable, right? So this is like a binomial random variable. And what was the probability that you would have I particles in the container? Let's start with that. Anyone remembers that probability? So it's like the number of successes is here having like I particles on the right side of the container. What was this probability?
Choose I
Well, it depends.
times.
Uh-huh.
Is it just the PMF of
Right. It,
the
it it was like n chooses I, right? Well, n where n was the total number of trials, right? Here, like n
right
is 2n particles, so it's 2n chooses I, right? Because you have to decide of these 2n I to go to the right side of the container, and then p to the I, q to the 2n
one
minus
minus?
I.
Yeah,
Uh, the thing is like here, P and Q are both one half, right? So it's like the perfectly symmetric Bernoulli binomial random variable. So it's 2n chooses I, one half to the I, and Q is like the complement, so it's also one half. So it's 2n minus I. So if you prefer, like you can write it this way, 2n factorial over I factorial, 2n minus I factorial, and 1 over 2i, 1 over 2n um, minus I. Okay. Um, so of course, like sorry, and maybe just to finish this 2i cancels this 2 to the negative I. So you can, if you prefer, you can write it as 1 over 2 to the 2n factorial over I factorial 2n minus I factorial. Is that making sense? So far, so good. And so this was the probability of having I particles on the right side of the container. So is that okay with everyone? So now, for this binomial random variable, what was the expected value of the binomial random variable? Anyone remembers this?
Was it 2n times p times 1 minus p?
Well, you're close. Yeah, it is. It was for a single Bernoulli variable, it was p. For a single Bernoulli random variable, it was p. Now you have 2n of those, so it's actually 2n times p. Uh, so it is 2n times one half, so it is just n. And this is where you have to think that this kind of makes some sense physically, right? Because if you have 2n particles and there's equal chance for each of them to be on either side of the container, that this is saying that on average, there's like kind of like half of the particles are on the left side and half of the particles on the right side. Is that making sense? Uh, so that is that is like a reasonable that's like a reasonable thing to expect, right? Because everything is perfectly symmetric. So if you knew nothing about anything, you would say, well, maybe there's like a, half, it should split half and half, right? So because of that, it's better to think of it's better to think of it's better to it's better to rewrite this expression. I'll think about I in the following. I'll write I as n plus m. So that way, I kind of think of it as the number of. So here, like that way, I'm kind of measuring I with respect to the average value, because that way m will be kind of like the number of additional particles above average that are on the right side of the container. Okay, so here m will be the number of particles above the average. Above the on the right side of the container. So it's kind of just to make it more symmetric. I'm symmetrizing it, like in a way, like it's better to measure like the quantities with respect to the average than with respect to zero. It's more natural here, the number n. So if you do that, the probability, just like you can think about it like the probability as depending on m. And so it becomes 1 over 2 to the n times 2n factorial times I, by I am writing as n plus m factorial, and 2n minus I. What is 2n minus I? Well, if you subtract I from 2n, you get n minus n. So like here, like, if n equals 0, it's kind of, you have exactly 0 particles over the average on the right side. So it's kind of like split evenly. If m equals n, that means that all the particles are on the right side of the container. And if m equals minus n, that means that all the particles are on the left side of the container. So like now n plus m is the total number of particles. So n plus m is the total number of particles on the right side of the container. Is that making sense? So it's just like a convenient, it's like a convenient way to compute this probability. It's like more like in the more like symmetric with respect to the average, which wasn't the case before. Okay. So now what's going to happen is that I'm really interested in these coefficients when n is extremely large, right? So in a sense, I want these coefficients when n is kind of going to infinity, okay? So I want these coefficients, I want these probabilities, I want to know these probabilities when n is extremely large. Again, like in our applications, like you would think of n around 10 to the 24. That's the sort of like number that you deal with like with macroscopic systems. So that what that puts you is into the regime of the Stirling approximation. The Stirling approximation is an extremely convenient approximation to the factorial. So because the thing is that you cannot just take like a crazy you cannot take like just like a crazy limit as n goes to infinity here. If you try to do like something like n goes to infinity here, like it's not so clear what you're going to get. You cannot just like attack the problem so directly. You have to like sneak in and do it like in a more subtle way. So the more subtle way is doing the Stirling approximation. So here's like which I don't know, maybe some of you have seen before, but it's like a nice approximation. Let's see. Why is this now not letting me to? Okay. The Syrian approximation, basically what it says is that it gives you like an approximation for the factorial, and it says that f factorial is can be approximated for n large by n over e to the n times root of 2 pi n. Okay. So is that okay so far, so good? So, and here, like, you might say, I should put like for n large. So you might say, well, how large is n large, right? Like that's something you might be interested in. And like the idea is that actually this approximation already starts getting quite what becomes really good already for like what you would consider small values of n. So for example, let me just show you that on Wikipedia. Where do I have this here? Here it is. Yeah, if you Google like, I mean, if you just Google the Stirling approximation, like you can find on Wikipedia like a graph like of n factorial. I don't know if you see it here. Like n factorial is like the blue curve. Okay. So like it's n factorial is discrete, right? So here it's just plotting some values for n factorial, and the pink curve is kind of like root of 2 pi n over times n divided by e to the n. So they're like, if you want something like the graphs look very similar, but there's like, you can see it more like numerically what's happening. So for example, if you plug in like if you plug in already n equals 10, so 10 factorial is this, and the Stirling approximation is this. So it's like an error of less than 1%. And already for n equals 100, well, first for n equals 100, like just look how gigantic these numbers are. Now you're literally talking about a 10 to the 157, right? Like that's like a 10 followed by 157 zeros. That's how much, like that's how big these numbers are with the factorial, right? Like it's an extremely big number. And like, like if you put the Stirling approximation, you cannot almost like even tell the difference. Like you would have to compute it like more carefully, but it's like less than 0.1%. So I'm just saying already even for 100 is a pretty, I mean, even already for 10 is like a pretty darn a good approximation. And here you're thinking about putting like n equals 10 to the 24. So imagine like how much better this gets. So it's like sometimes like that's kind of like the funny things with these approximations. And sometimes you say, well, for n large, and you think, well, then n must be huge. And many times like they start working pretty well, even for low values of n, like way lower than you would expect. So it's kind of like it's also like you can also check like the comparison with the logarithms. So like since the log grows slower, then like the approximation does require like larger numbers, as you can see here. So if you wanted also the natural log to be natural log of a factorial to be well approximated, you would need to take bigger values for n. But even then, like it does get pretty quickly to like a good comparison. So I'm just saying that this is like a really, really good approximation. Okay. So you shouldn't feel bad in using it. Like you're learning it is like a safe approximation to use. It's just that it is so much easier to work with with powers of a number than with factorials. That's what makes this approximation convenient. Okay. Is that making sense? So let's just try to apply this Stirling approximation. And why is this also like a good way to rewrite the probabilities or these factors? Because if you write it with if you write it in this way, um, in where n appears explicitly in both terms, like here you have to imagine that little m is fixed. So this number is the one that you're changing and you're fixing little m. So this will be like a very large number, this will be like a very large number, and this will be like a very large number. So each of these are, you know, kind of like well approximated by the Stirling approximation. So let me just put that here. So what would be the approximation for, I'm just trying to see, oh, here it is. So what would be the Stirling approximation? So let's use Stirling. So 1 over 2 to the n, I don't want to touch that because that's already in power notation. So this is good to go. 2 to the n, the first one, I'll replace it here. So I'll put like, right, so just put n equals 2n. So you get 2n over e times 2n root of 2 pi times 2n, right? That's what the numerator gives you. And then you're dividing this by each of the other ones, right? So now it's the first factor becomes like, let's use a different color here. So it becomes yeah, n plus m over e to the n plus m root of 2 pi n plus m. And let's do the same thing for the other one. So if you get n minus m over e to the n minus m times root of 2 pi n minus m. Is that making sense? So that's what you get if you apply the Stirling approximation to all of them. So what's the first thing that you can notice? There are a couple of simplifications that already start happening here. So the first thing you can see is that like the stuff that has like e cancels out because here you get like e to the 2n, and here when you multiply the exponents, right? Like these two exponents they add up to 2n, right? So the same factor of e appears everywhere, so that goes away, which is nice. So you get 1 over 2 to the n. Okay, so let me put like, it's kind of better to break this into two pieces, like the stuff um with oh, there's another simplification that happens, sorry, before continuing. Right, because if you what's another simplification that happens here, which is easy to see. If you let me find the right color. Let me put orange. If you raise 2 to the 2n, right? If you raise 2 to the 2n, that's precisely what you get here. So that also goes away, okay? Is that making sense? So what survives here is n to the 2n, right? That's like what you get from here. Let me put the other one in purple. So like you get n plus m to the minus n plus m. Then the n minus m to the n minus to the minus n minus m. And then you also have this stuff that has a square root. So you can there are a couple of things that you can simplify here as well if you want. Yes, let's see how many, let me check how many steps I want to give. Like, for example, you could cancel out this root of 2 pi with this root of 2 pi, okay? And then, so you can write it as root of 2n over root of n plus m. Let me, to make this more symmetric, I'll take out this root of 2 pi outside, so. Oh, and then, yeah, so, sorry, there's a 2 here that can cancel, so there's a 2 that you can cancel here, so you also don't need this one. Okay. Whew. So we're on the right track. So is that making sense? So far, so good.
In the top row now, you can multiply like the n plus m to the negative m, and then the n minus m. Actually, that might not.
Yeah, it's no, you just have to. I mean, it can be simplified further. Let me just like see how should I do it. So you can okay. Yeah, you like the idea now is to factorize an n on each factor. Like so, let's continue with this approximation. So let's keep this. Like I'm going to go slowly. So n to the 2n. Like if you factorize an n here, you get n to the minus n plus m, right? And then this gives you 1 plus m over n to the minus n plus m, okay? And then if you do the same for the other one, you get n to the minus n minus m times 1 minus m over n to the minus n minus m. And you see, if you do the same, you can do the same in each factor here. You can pull out you can factorize a big N, right? When you factorize a big N, you get, one of those cancels this one here. So you can just put like root of pi N and then root of 1 plus m over n times root of 1 minus m over n. Is that making sense? Whew. So yeah, like now what would happen next what will happen next is that if you count powers, when you multiply this thing with this thing, the n's cancel, so you get n to the minus 2n, which cancels this precisely, okay? So you get that, and okay. And then I'm just going to break this into this very convenient way to put it. I mean, this is definitely like an approximation that you have to write before explaining it, because otherwise you would get stuck on how to do it. It is like a tricky manipulation. Like, it's like a fun thing to work, but you do have to kind of know where you're headed, because otherwise it is like, it can be quite the challenge. So. Right, so I just broke these into two products so that I'm keeping the factors with minus n appear first, and then I put the leftover on the right side. And then like you can also, I mean, it's kind of, you'll see, like I won't care too much about this term either. So let me just combine them into a difference of squares, because that's actually what I'll do in the other one. So these two square roots, like you can combine them as 1 minus m squared over n squared. That doesn't matter too much. Like you'll see, I won't care too much about that one either. And so, and then is that making sense? And then like I'll like, yeah, just to maybe put this in a different color, I'll combine these two as 1 minus m squared over n squared to the minus n. And then I'll keep these other two here, 1 minus m over n to the minus m. 1 minus m over n to the n. Okay. And then you get the root of pi n, root of 1 minus. Okay. And then we are almost done. So what I'm going to do next is just like, again, you have to imagine that n is going to become really, 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 really large. So what's going to happen here is like, this is like a very small number. M over n, like you can call it alpha if you want, or like, yeah, let's call it alpha. It's going to be really small. So like what's happening here is like we did this once, like on the birthday problem, like long time ago. You can use like the approximation that e to the alpha is 1 plus alpha, or e to the minus alpha is 1 minus alpha. So I will apply those I mean, and I'll apply it also for like I'll apply it on the for each of these terms. So the blue one will become like, just think of alpha as m squared over n squared, so it becomes e to the minus m squared over n squared. This is raised to the minus n. And the other one will become e to the m over n raised to the minus m. And the other one will become e to the minus m over n raised to the m. Is that making sense? We're I don't know if you see our good friend, the Gaussian, is starting to appear already, right? I mean, it may not be so clear, but it will appear very soon. So, like, you know, you have to be careful when you do this, but when you raise these exponents, like you just multiply them, so you get e to the m squared over n, and here you multiply this one and you get e to the minus m squared over n, and here you get this one, which is e to the minus m squared over n. Right, and I guess, let me see if I want to do that one here as well. Oh, yeah, you can do it here as well. Sorry about that. Let's see if this, like, I can. right? And then this goes away, and you can recombine these two. Oh, when you take square roots, I mean, okay, sorry, I have to take yeah. Okay. Like this is fine. Let's see. Okay, this is okay. The thing is like if you like okay, this is fine. Like the thing is like if you notice this, right, I did this correctly. So this one, what's the difference between this exponent and this exponent? The difference here is like n just appears, it only appears as n. On the other hand, here the n appears in the denominator as n squared. So if you were to compare both exponentials, this is overwhelmingly smaller than this one. You see, because like here n like appears squared, so the denominator, like the overall fraction, is a lot smaller. It's like the overall fraction is closer to zero. So in a sense, you can kind of, if if you want to kind of just get the like the standard exponential, you can just you can just clip the numerator, because this this fraction, like this exponent, is closer to zero a lot faster than the other one. You see, so that's why, I mean, usually when you do this approximation, you kind of ignore like this to begin with, and so that's how you end up with the famous factor root of pi over n e to the minus m squared over n. And that essentially, if you compare it to, let's compare this with the Gaussian. Well, if you compare this to the Gaussian, what that tells you is that you should make n equals 2k, take n to be 2k. But in other words, 2k, if you remember, was like the standard deviation square, so it's 2 sigma square. So in a sense, like sigma, the standard deviation is root of n over 2. Okay, so like that means that the binomial distribution in that when n gets sufficiently large, it becomes a Gaussian distribution where like the standard deviation is proportional to the square root of the number of particles. So let me write that down in words. So in when n is really large, so like the important thing of this result is that the standard deviation is proportional to the square root of the number of particles you started with. Okay. So let me tell you why that's important. Like, and this will show you like why working with large numbers makes such a crucial difference. So there's like a fact that I didn't say, like I didn't write like last time about the Gaussian, but so for the Gaussian, you have this standard bell-shaped curve, like because this one is centered at the origin, so it really looks perfectly symmetric about the origin. So this is like the usual Gaussian, like the standard Gaussian with. So this is like a Gaussian center at the origin. With standard deviation sigma. So there's like this famous result that this is that the probability, like for example, that the probability. Let me put it for the way which is usually like given. So there's this famous thing, property of the computational result about the Gaussian, that the probability for the standard Gaussian for the values of x to be between sigma and sigma, that like the probability that the values are between sigma and sigma is 0.68, roughly 0.68%, or 68% roughly. And for the random variable to take values between minus 2 sigma and 2 sigma, that's already like 95%. That's where like this confident test of, sometimes you may have heard like this 95% confident tests. And that's kind of like, that's what it means. That like you would, like certain values lie within 2 standard deviations of the average. Like,
I have a question.
Yes, sorry, yes.
You like I would expect like if the number of trials increases, that my uncertainty would decrease. So, but this is saying that the uncertainty is proportional to n the number of trials. So if the number of trials increases, your uncertainty also increases?
Well, you have to be careful. Okay, this is where we have to discuss this. It is proportional not to n, but the square root of n, and that makes a huge difference. So okay, like yeah. I mean, this is of course like right, like this can seem paradoxical, but it's less paradoxical once it's put in the correct context. But yeah, but it's a good observation because it can be confusing. I agree. But I'll explain why it's less confusing than what it seems. So let me just finish writing this. So this is saying that, but it's so this is saying that within 3 standard deviations on either side, there's a almost 99% chance like that the values that the random variable takes in the normal Gaussian to be between 3 standard deviations. So for example, what does this say in our case, right? So here, like as you noted, the standard deviation is proportional to the square root of n, right? So that means that there's a so in our case, there is almost like a 95, at least a 99% chance that the is between n minus 3 sigma and n plus 3 sigma. Because remember, I mean, this is kind of like, I kind of center everything at the origin, but there's like an overall shift because like really the expected value for like the number of particles was n, right? So what this is saying is like, there's a 99% chance that the number of particles on the right side of the container is between n n was like the half of the number of particles, so that makes sense. So between n minus square root of minus 3 square root of n and n plus 3 square root of n, there's a 99% chance that the number of particles on the right side of the container is between those two values. Okay, but here it's important to understand like the numbers we're talking about. So for example, if you think that n is about 10 to the 24, right? So you're talking about, you're saying that the number of particles is between n minus 3, 10 to the 12, and 10 to the 24 plus, let me put 3 times n to the 12. That these number of particles, you're saying that with 99% chance, the number of particles on the right side of the container is between 10 to the 24 minus 3 times 10 to the 12 and 10 to the 24 plus 3 times 10 to the 12, okay? But now, and this is kind of hopefully related to your question about like the uncertainty in growing, like when you, like what you really should compare is not like the total amount of uncertainty, but kind of like the uncertainty like per number of particle in a sense, or like the uncertainty compared to the average value. So now, like, how much larger is this compared to the average value, right? So if you look these, like the right comparison is not too, what I'm trying to say is that if you plug, like, if you compute 10 to the 24 minus 10 to the 12, like that number is more or less 10 to the 24. Like this looks huge, but it only looks huge because you're not realizing you're comparing that against 10 to the 24. So if you actually do like a fractional uncertainty, like compared to the average value, where it's like 10 to the 24 minus 3 10 to the 12. Well, let's put it plus minus 3 10 to the 12 over 10 to the 24. Like that is like 1 plus plus minus 3 to 10 to the minus 12. So like, these values, they are basically indistinguishable. They're essentially the same as 10 to the 24. So it's saying that, right, as an absolute uncertainty, it looks like huge because as you were mentioning, it's growing with root of n, but it is growing fast. It's growing like as a square root of the actual number of particles. So per number of particle, the uncertainty is going to shrink, is decaying as 1 over root of n. Is that making sense? So I'm just saying, like, you have to be careful when you're thinking about it like as an absolute term. Yes, and as an absolute term, well, yeah, well, 10 to the minus 12, right, is, what's 10 to the minus, it's 0.0000000000001 or whatever, it's so small. So I agree that the absolute number, like it looks, it may look humongous to say you have 10 to the 12 particles more on the right side of the container, but that's only because you forget that you're comparing it against 10 to the 24 particles. Once you think about that, adding that is like adding like, it's like if I told you, you have $1 billion in your account, a hacker stole $1. I bet you no one will care about this. You know what I mean? And we're talking about numbers that are even more like absurd. Like $1 billion with $1, I think it's not even that, because $1 billion is what is 10 to the 6 or 10, like 10 to the 9. So it's even like bigger than that. It's so unnoticeable that for all practical purposes, it's kind of like the number of particles almost remain at half number of the number of particles on the right side of the container is more or less roughly always like half the number of total particles, because adding 10 to the 12 plus or minus a factor of like a constant times 10 to the 12 is nothing. Like, is that making sense?
Yeah, that makes sense.
So it's just, in fact, like this is actually philosophically very important. This is saying that even if there are fluctuations, this is actually related to the question at the beginning of the class about this approach to the equilibrium. So it's not that we're making the claim that the number of particles is always like half and half, right? But what we're saying is that any deviation from the average, right, is so absolutely small that for all practical purposes, you would not be able to notice it, right? So you could add literally 10 to the 12 particles to one side of the container. That's nothing because because that grows with the square root of n, right? And the total number of particles is n or 2n. So it's kind of like saying that the fluctuations, the fact that the fluctuations grow with the square root of n looks like a lot, but it's only because you're not thinking about it as a fraction. So as a fraction, it's actually decaying, right? So if the fluctuations are like proportional to square root of n, so like the fraction of fluctuation or like the average fluctuation, right? Like the fluctuation from fluctuation per particle, if you want to call it like that. I don't think that's like a standard name, but it would be like root of n over n. So it's actually decaying like 1 over root of n. So it actually, like the fluctuations are actually very, very small. And that's why in all these questions about chemistry, like thermodynamics, like you can think that in many situations, equilibrium is achieved very quickly. So like the classical problem with thermodynamics, I don't know, is you have like a gas with a container, you have like a wall in the middle, all the particles are on one side of the container at the beginning of the problem, and then you release the wall in the middle. Like the amount like of time that it would take for that system to reach equilibrium is very short. And in the end, like what happens is that there's like the overwhelming majority of situations will be so little away from the equilibrium. Equilibrium, I just mean here like the average value, that for all practical purposes you could never notice it. It would take like a very, you would have to wait like a humongous amount of time. When people do these calculations, it's like larger than the average like life of the universe. So billions of billions of billions of years to ever run into a situation where all the particles miraculously decided to, just by fluctuations to go back to the beginning where like they were all on the left side of the container. Those events like are just like occupy, so there's just so little chance of that happening that it's almost as like, like again, like 99% of the time you are almost within like the average value. So that's actually why what happens in statistical physics, sometimes you kind of just assume that the value of your physical quantity is the same as the value of the average value, because any deviation just decays so fast, so quickly with the number of particles that, it's nothing to be worried about. So that's kind of the power of like large numbers, right? Once you have large, like if you only have 10 particles, then you better be, yeah, this doesn't hold, right? Because square root of n is very comparable to square root of 10 is very comparable to 10. Like, so you really have to be careful. But once you're talking orders of magnitudes, high powers of 10, like it's just so small that like almost like all the fluctuations like kind of go away. Like they're almost like imperceptible. Although it's like, yeah, at the beginning it can seem very like very counterintuitive that it was growing, but it's just like from a different angle, it's like almost nothing. So that's kind of like, yeah, and it's kind of cool to do explicitly to see how the quantity is proportional to the number of particles. So that explains a lot. That explains like a lot of stability of macroscopic properties, because like then the fractional decrease of the fluctuations is with 1 over root of n. So like the fact that the growth rates are different, like it just like makes a lot of like things work. So it's like a cool thing to see. It's nice directly. Is that making sense? So yeah, it also shows you how the Gaussian kind of appears in a very elegant way from the binomial distribution. And yeah, so this kind of, I think, is more or less everything that I wanted to tell you about the binomial distribution for now. Because as I said, there's still a couple of things. Once we discuss the central limit theorem, like it will reappear, but hopefully it gives you like a better perspective of why it's important, an important distribution. Okay, so is that okay? Are there any questions before? I'm going to switch a little bit of topic, so just making sure there are any other questions about this. Okay, so yeah, so the last thing that I want to say is a little bit about the distribution function of a random variable, because it's useful, and that's related to the problems I deleted for the quiz from today because I realized I cannot cover them. So it's slightly different. Okay, and we also have a quiz in a couple of minutes. So let me just tell you some quick stuff about it because it's relatively straightforward, but it's still nice to see explicitly. So let's talk about the distribution function. So if you remember so far, when the random variable has a density, like up to this point, we have been speaking about the density function of a random variable. Density function of a random variable. And the density function has like the key property, right? That the probability that the random variable takes values between x1 and x2 is just the integral from x1 to x2 of f of x dx. Okay, so that's like what makes the density function a useful thing. There's another thing that you can define, which is called the distribution function. Which is just, usually the name that is given to it is uppercase F. That's just a probability that the random variable is less or equal to X, okay? Which if you write that as an integral, like that just means that I'm just fixing the upper bound. So like strictly speaking, like if you just want to write it directly as an integral, it's just like the integral from minus infinity to X of f of x dx. At this point, like you may get a little bit too concerned about using both the variable x as the upper bound and as a variable of integration. So, you know, for mathematical purposes, it is like a little bit better to just change the variable of integration. But like, you know, it's not that it would cause them many issues, but it is better sometimes to write it with a different variable. So it's like you just integrate the density from minus infinity to x. So this is kind of like the probability up to value x, right? So this is just the probability x is on the interval okay, and so then the thing is like in practice, like, you know, obviously if you know f of t, you can figure out f of x, right? So like the problem is that both have the same name, just one uppercase and the other one lowercase. But like if you know f of x, then you can find big F, like the distribution function. But the converse is also true, right? If you know, but like the more interesting thing is that if you know this uppercase F, but if you know uppercase of x, you can find the density function. How can you do that? Well, it's just a fundamental theorem of calculus, basically, right? So the fundamental theorem of calculus says that the derivative of big F with respect to x, right? I don't know if you remember, like, it's something that you use a lot in Calc 1 near the end of the course, but you kind of stop using that but it's kind of implicit in many things that you do in Calc 2 and Calc 3. So if you remember like the fundamental theorem of calculus, what it says is that if you take the derivative of this function with respect to x, kind of like the derivative kills the integral, so you're just left with f of x. Okay, so if you know the distribution function, the density can be found by taking derivatives. Is that making sense? And that is convenient in certain problems to find. That's convenient in certain problems if you want to find the distribution, the density function of functions defined in terms of x. So let me tell you like some applications of this idea. So this can be used in practice to find density functions. And this is related to the questions on the quiz that I deleted. So that's why I needed to do this first. So for example, let's start with something easy like example. Let's say you have like a random variable. You have a random variable x. And we did this one before, right? We had defined, once you have the random variable x, you can define like a translate, right? Like, so let's define like a translate from it, a translate of x as y. Well, not a translate, like a dilation plus translation or rescaling. Let's just use the word rescaling. Right, we had considered this before. Let's just say that it's not like a big restriction, right? But let's just say that like A is positive. We're with A positive. So let's say like the question would be like find the density, like if you know the density function of x, what's the density function of y? Is the question making sense? So it's just like how to relate the density functions of two random variables that are related by some equation. So let's try to think about that concretely. So what does it mean to have like the density function of x? That just means that the probability, which is the probability that x is less or equal to x, is just the integral from from negative infinity to x of f of x, f of t dt. In this case, if you want, it might be useful also to, you do want to introduce some extra notation to indicate that this is like the density function of x. So you can call that something like this, f sub x of t dt. Okay, so just to emphasize that this is the density function of x, and like, again, you can call this, or well, we could call it f and g, maybe. Okay, let's, because this is maybe too much like of notation. Okay, and then so this f is the density of x. And then you would want like the density of y is going to satisfy the following. So it's kind of the same as we were doing before. Like it's convenient to call like the values that y takes y. So you can call this like g of y would be the probability that y is less or equal to y, and that would be the integral from minus infinity to y of g of t dt. Is that making sense? So I'm just saying like this is what the property that the density of y would have. But once you do that, it is not so difficult to solve, because what's the probability that y is less or equal to y? Well, that's the probability that ax plus b is less or equal to y, right? So just kind of solve this inequality for x. So that's a probability that ax is less or equal to y minus b, and that's the probability that x is less or equal to y minus b over a. Is that making sense? And that is equal to the integral from minus infinity to y minus b over a of f of t dt. Is that okay? Everyone good with that?
Yeah, that makes sense.
And then the density of y would just be the derivative of this function, right? So the density of y, if you remember, like the density, that's like what I mentioned this before. The density is just the derivative of this distribution function. So the density of y is just going to be the derivative with respect to y of this integral. Okay. The only thing is that you have to be careful again, like if you remember how to do this with the fundamental theorem of calculus. In Calc 1, you do this a little bit. You cannot just apply the fundamental theorem directly, because the fundamental theorem only works when the variable on top is exactly the same variable. But here, if you don't have just y, you have like y minus b over a. So if you want, you can do like a u sub. I mean, like, unless, in case you forgot about how to do this. So you call this like a u sub. So like you are finding the derivative with respect to y of the integral from minus infinity to u of f of t dt. And then you apply the chain rule. This is the derivative with respect to u of the integral from minus infinity to u of f of t dt times the chain rule, which is du dy. Okay. And that gives you what? It gives you, now this is f of u times the udt. And what is the udt? That's just 1 over a. So this is just what is u? F of y minus b over a times 1 over a. So the density of 4y is just g of y is equals to f of y minus b over a times 1 over a. Is that making sense? So it is it's a funny combination of like, playing with some inequalities and a fundamental theorem of calculus. I'm about to do another example, but to see if this is making sense. But
Professor, I had a question real quick. Yeah, 1 over a.
Right, because like what? Oh, the 1 over a is in front of the function, right? So, but yeah, because like I have to. Let's see. Because I have to multiply by the derivative of u with respect to y, right? When I use the chain rule.
Gotcha.
Is that making sense? Yeah.
That makes sense.
So it's kind of like that's like the rescaling that goes there. But so that's the one. Okay. So let's do another one. Before moving to the quiz. So imagine here's another example. I tell you that I have a random variable with density f of x, and now I define y to be e to the x, the exponential of this random variable. So what is the density for y? Okay, so again, what does it mean for x to have density? What does it mean for x to have density f of x? That means that the probability that x is less or equal to x is just the integral from minus infinity to x of f of t dt. And what would be the density for y? It would have the property that the probability of y less or equal to y, it would be that the integral from minus infinity to y of t dt. Okay, so this is like the property for the density of x, and this is the property for the density of y. Okay, but again, you just work out what that means. So what's the probability that y is less or equal to y? Well, that's the probability of e to the x less or equal to y, right? And so when can that happen? That happens whenever you can apply natural log on both sides of the inequality. Natural log preserves the inequality. So you can say that x is less or equal to ln of y. Okay. But again, this is just like equal to the integral from minus infinity to ln of y of f of t dt. So that means that the density of y is going to be the derivative with respect to y of the integral from minus infinity to ln of y of f of t dt. And here maybe it's more clear that you cannot just apply the fundamental theorem directly, because like to apply the fundamental theorem of calculus directly, you need this to be y. So again, you make a use of, you can make u equals ln of y. So this is the derivative with respect to u of the integral from minus infinity to u of f of t dt times the u dy. And that gives you f of u. What's the derivative of u with respect to y is 1 over y. And what is u is ln of y. So it's like the density. So the density for e to the x, the density for e to the x is like f of ln of y divided by y. Okay. So I think in one of the problems that I removed for the quiz was I gave you like a random variable with a certain density, and you had to find the density of another random variable base constructed out of it. And so that's kind of how you had to do it. Like that's how like the way in which we will find these densities. Like you kind of have to relate the distribution functions, and once you can relate them, you can just take the derivative and use that fundamental theorem of calculus. Okay. So yeah, but it's like a fun trick to keep in mind um in general. I mean, yeah, I guess after on next week on Wednesday, I may say a little bit more about this, but at least I wanted to show you some ideas of how this works in practice, if that's okay. Is that making sense? Are there any questions about this? So basically, if we exclude the days we have exams, like I did the count, we have like 6 more lessons. So essentially for this class, the only thing that's left is multiple random variables. How can you talk about multiple random variables at the same time, which is kind of cool topic. That's where like double and triple integrals will come in also. So multiple random variables, and once you have that in place, you can also discuss like the big theorems of probability, which are like the Strong law, the law of large numbers, and the central limit theorem. So we already got like a snippet of the central limit theorem, where like the binomial, the Gaussian or this normal distribution kind of appeared out of the binomial. But yeah, the central limit theorem um, is kind of like what kind of justified in many statistical applications the use of the normal distribution as like the go-to distribution. Um, so it would be fun to go over that. But yeah, so it's kind of like those two big topics that we have left. So I'll try to, I think we'll get a chance to cover all of it. But of course, like, the book has so much information. It's almost 300 pages, like the 8 chapters that we're supposed to cover. So I'm like, there are things like that I'm just simply skipping over because like it's not essential to the big ideas of the course. But of course, you should read it if you want to learn more about it. Like, hopefully the idea is like the course like catches your attention, you notice that probability theory can be useful, and then you could just read more if you are interested. But yeah, there are too many details to go over. So I'm just kind of like saying like the most important things, or like what I consider the most important things, to give like a big picture of what's going on, because like the book is just so full of details. So but yeah, so that's kind of what I wanted to say for now. I think it's a good moment if we to let's see, is this someone that I'm yeah. So yeah, if I think we can start taking the quiz if you want. As always, like just upload your solutions to Grayscope once you're done. But if you don't have any other questions, you can leave now, and I'll just make the quiz available for you to take at the moment. I'll see. Well, I guess the exam is on Monday, but yeah, I'll be around on Monday in case something comes up and you have an emergency. You can email me during the exam or whatever. But physically, I'll see you on Wednesday, I suppose.
Thank you, Professor. Have a good weekend.
Okay. You too. You too. See you. Bye.
Thank you, Professor.
Bye. 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 No problem.